This video is a discussion of slides 67 through 90 of Chapter 1. The topics include the nature of molecular orbitals as it relates to bonding in organic molecules. We will discuss the mathematical description of bonding molecular orbitals, its early origins from wave functions, through its culmination in hybridized molecular orbital models that we use today to describe molecular bonding in organic molecules. If we look at two models that describe atomic orbitals, that means no bonding present, it's just the carbon atom all by itself. We have the Bohr model, which we still use today to describe and to explain certain chemical phenomena. We look at the Bohr model and we see that it has two shells. The innermost shell has 2 electrons around it. The outermost shell has 4 electrons around it. This nicely explains that in order to fulfill my octet, I need to get 4 more electrons from somewhere, so I share them with 4 other atoms, or I form double bonds or triple bonds, and I fulfill my octet. We also have the quantum mechanical model. Again, this is for atomic carbon, isolated carbon by all itself. We still have 2 shells. We have an inner 1 shell, which has only a spherical orbital, and we have a 2 shell, which has 2 subshells. We have a spherical subshell called 2s, and we have 3 dumbbell-shaped orbitals that we're going to call px, py, and pz. Again, we use this model to explain organic chemistry, some parts of it very well too. Let's look at the origin of the quantum mechanical model. Okay? Quantum mechanical model predicts that the probability of finding electrons around the nucleus occurs in certain orbitals, those spherical ones and those dumbbell-shaped ones, and it describes them as a probability so that we can look at them as a snapshot at a certain time. Mathematically, the equation is quite complex. Schrödinger actually took Maxwell's original equations that had to do with light and applied them to electrons. He said, I believe that electrons behave as light too, which we know we can describe by wave functions, meaning we have amplitudes, we have wavelengths, and we have frequencies. If you do the mathematics and put in the masses of the electron and a few other things, you get the Schrödinger equation, which again is fairly complicated. But what you find is that for these different shells, you get different wave functions for each of the different shells. Rather than them just being orbitals like Bohr predicted, they actually have structure to them. The one shell has a very simple wave function, and this is just depicted in 2 dimensions now. In 3 dimensions, it would be a sphere. The 2 shell has, in addition to a 1s function, it has a bimodal wave function, which looks like in 3 dimensions, that looks like a dumbbell. If I look just at the 1s shell, I can see that I can either have a deflection in the positive direction and an amplitude d, or I can have a deflection in the negative direction with an amplitude d, and those are oscillating between each other as light would. So electrons can oscillate as light does. We typically call these oscillating displacements the different phases. So you notice there's a positive here. That's just a mathematical positive. It's not charge, it's not an ion. And here is a negative displacement, and so it's a mathematical description of the displacement. So we can treat these orbitals as standing waves in 2 dimensions, or we can look at them in 3 dimensions. If we look at them in 3 dimensions, they look like a sphere with a phase, again, positive phase, or a negative phase represented by the green negative, or the blue as a positive, Again, these are not charges when we're talking about the mathematics. If we look at that in just 2 dimensions, meaning we take a slice through that sphere, we can look at the electron density, and the mathematics predicts that we have our highest electron density in the 1s shell right at the nucleus, or we have a wave function that predicts we have a negative phased electron density at its highest amplitude at the nucleus again. So we're plotting the distance of electrons from the nucleus, and we call these 3-dimensional depictions here as orbitals, and they're just the probability function of where is it most likely the electron will be mathematically put into 3 dimensions. If we extend that to the p orbitals of our quantum mechanical theory, we see that in 3 dimensions we get these lobes, which have phases also. It's a positive phase and a negative phase. It could also be the other way around, where we have a positive phase on the left-hand side and the negative phase on the right-hand side. If we were to take a slice right through these 3-dimensional orbitals, we would see that we get in 2 dimensions. It looks much like a wave of light, a sine wave going through those space. Again, negative phase, or positive phase and negative phase. Notice there is a node in these p orbitals, so there's a nodal plane where the amplitude is always 0. Meaning that if I have a probability somewhere the electron is going to be in this node, it could either be in the negative phase or a positive phase there, and somehow the electron gets from the positive phase over to the negative phase. So this picture still doesn't quite explain how electrons get between those phases. And we can now extend that description of the atomic molecular orbitals and look at molecular orbitals, which just means the combination of atomic orbitals. How do atomic orbitals overlap mathematically to form bonds? So this is what we're going to call molecular orbitals now, or a molecular orbital theory. So if I look at carbon, which has 3 valence orbitals, a 2s, a 2px, a 2py, and a 2pz, I add to that 4 hydrogen atomic orbitals, a 1s, a 1s, and a 1s, and a 1s. They can overlap to form this CH4 bonding orbitals. But how does that happen? Okay. We still need to look at a few more concepts before we can explain this phenomena. One is that we have conservation of orbitals. If we have 4 orbitals from carbon and 4 orbitals from the 4 hydrogens, we still need to have 8 total orbitals in our molecule. 1, 2, 3, 4, 5, 6, 7, 8. The waves that are in phase add together. So this green 1s orbital can interact with a green 1s orbital. The green can interact with green. So only orbitals that are in phase can add together and increase their amplitude. Whenever you have increased amplitude, you can form a bond. It's a more stable energetic situation. Waves that are out of phase, they actually cancel each other out. Let's look at some of that in the next slide here. So, if I look at a very simple combination of atomic orbitals, I have a spherical orbital, a 1s orbital. If I combine that and start moving this 1s orbital closer to this 1s orbital, if they're in phase, they combine and form a more stable structure. That overlap here is considered a bond because it's more stable. It's more stable to be closer together than it is further apart, and it's got 2 electrons in it. If they combine, if one of these is out of phase and they combine, I literally get an anti-bonding molecular orbital, and there is a node between those because one is out of phase and one is in phase, and that's energetically non-favorable. So bonding molecular orbitals are lower in energy. Anti-bonding molecular orbitals are higher in energy, but I have conservation of energy. I start out here at one level and those orbitals go down the same amount as those goes up, so I don't have a net change in energy. If I look at bond formation and I look at a two-dimensional description, so I'm now looking at the atomic orbitals of 1s in 2 dimensions here, as I start moving those 1s orbitals closer together, I tend to build amplitude here in the middle. I get higher amplitude, and that is depicted here. If I were to look at anti-bonding orbitals that are out of phase, I start bringing them closer together. They destructively interfere, and so I have no amplitude gain here, and I have what we call an anti-bonding molecular orbital. So when two 1s orbitals overlap out of phase, they interact destructively to form an anti-bonding molecular orbital. For example, this would nicely explain how hydrogen atoms combine to form hydrogen gas H2. I can do the same sort of arguments with the p orbitals, the px, py, and pz. Right here, I'm only going to look at the px orbitals. If I have head-to-head combination where I have the positive phase getting closer and closer to a p orbital of another atom, if I get them closer and closer, they will constructively add to form a bonding molecular orbital. If they get closer and closer together and they're out of phase, they will form an anti-bonding orbital. This is higher in energy. The electrons will be in the lower energy state. So, anti-molecular bonding molecular orbitals are higher in energy than the bonding molecular orbitals. Okay. I could also overlap a p orbital with an s orbital. For example, if this is one of the p orbitals in carbon and this is an s orbital in hydrogen, they can constructively add together to form a bonding molecular orbital. And conversely, if I have a p orbital that moves closer and closer to an out of phase, a negative phase 1s orbital, those can do destructive or anti-bonding combination that is higher in energy. There is a second way that p orbitals can combine. If I look at the py orbitals in this case, I find out that if they move closer and closer together, these in-phase orbitals can constructively combine to form bonding orbitals, where the pluses combine with the pluses and the minuses, which are out of phase, combine with the minuses, and I get constructive addition and bonding. If they get closer and closer together and they're out of phase, I get destructive interactions and I form an anti-bonding orbital. This type of bonding is what we consider the second bond in a double bond or a triple bond. So this is called pi bonding. Now let's look how we can take those orbitals and actually make a molecule. So if I take the atomic orbitals in carbon, I have a 2s, a 2px, a 2py, and a 2pz, and I combine them with 4 1s orbitals of hydrogen, I should get this tetrahedral structure of methane. But those structures here, they don't look anything like a tetrahedral, and I also should be able to combine them to make the trigonal planar geometry of ethylene, where I have a double bond between carbons, and a triple bond in acetylene, where I have 180-degree bond angles, but that doesn't explain it well. So I need to do some more changes. I need to adjust my mathematics, and I do some hybridizing. So I take my original atomic orbitals and I modify the quantum mechanical model to account for the geometries of bonding that we know experimentally. Linus Pauling did that again, and he actually did this hybridized molecular orbital theory. So what he did is he took these 4 atomic orbitals, he hybridized them to form these 4 yellow ones, which are tetrahedral. He then did some other mathematics where he took three of these, the 1s, the px, and py, combine them mathematically and form these three yellow ones on each of the carbons here, and he left one unhybridized, and that's what forms the pi bond. He also then took this 1s orbital and one p orbital, combined that to form two new orbitals that accounts for that, and two unhybridized orbitals, this py and pz, to form these other two pi bonds. And it's all done by overlap again. If I overlap orbitals, I get bonding. Okay? So let's look at that again. For single bonded carbon, I take an 2s orbital, a px, a py, and a pz. I mix them all together mathematically to form four new orbitals. Each one of them is going to be called an sp3 hybridized molecular orbital. They're degenerate because they all have the same energy. If these four orbitals overlap with a hydrogen 1s orbital, I can share this electron, this electron, this electron, and this electron of the carbon to get four identical bonds. If I looked at them from an experimental standpoint, I see that they're 190.5 degree angle apart from the hydrogen carbon to hydrogen, which is tetrahedral. And that's exactly what the mathematics would predict. I would predict a tetrahedral structure for methane gas. Okay. So these are sp3 hybridized molecular orbitals. Atomic orbitals, hybridized molecular orbitals. So this same description does not account for double bonds, and so we do the math differently in this case. In this case, we take the 2s orbital, one of the p orbitals, a second p orbital, do mathematics on these three orbitals to form three new orbitals. We're going to call these sp2. S, a p, and a p combine to form an sp2, an sp2, and an sp2. One of those orbitals, this pz in this case, is unhybridized. So now if I look at my energy diagram here, I have my 1s orbital, which is still way down in the center. I have my four hybridized orbitals, which are for my valence electrons, one electron in each. The sp2 orbitals are lower in energy than the unhybridized p orbital. When I bring in hydrogen to these orbitals, I'm going to find out that I can bond literally three different atoms to these three orbitals. So I have a hydrogen, and a carbon. But I also have this p orbital, which is unhybridized, and that is this second bond here, which is the overlap of the pz orbital to constructively add here to form a second bond. So I have a sigma bond due to the hybridized orbitals. I have a pi bond due to the overlap of the unhybridized orbitals. I also still have my orbitals, my sp2 orbital overlapping with my s orbital of hydrogen to form another sigma bond, and a sigma bond. Geometrically, from the math, these should be 120 degree bond angles. That's what the math predicts. It's not quite that, but it's close. So if I look at hydrogen, carbon, carbon, I get about 121 degrees. That's because the electron clouds around those push these a little bit away from each other. If I look at hydrogen, carbon, hydrogen, I get a little bit less than 120 degrees. Right? So if I summarize that, if I look at hydrocarbons, molecules that just have hydrogen and carbon, where one place between two carbons there's a double bond, one of those bonds is a sigma bond, and one of those bonds is a pi bond. Sigma bonds and pi bonds. And the analogy goes on for triple bonds. If I take the 2s orbital and combine it with just one of the p orbitals, in this case I'm using the px orbital, I hybridize them mathematically, I get two new sp orbitals, and those are the ones that account for sigma bonds. I have now two unhybridized orbitals which can combine mathematically and overlap with other molecules to form more bonds. So if I go way down here to the bottom corner, if I overlap the sp orbital of one carbon with the sp orbital of a second carbon, I form an overlap, or constructively adding those two together to form a sigma bond. I take the other sp orbital, overlap it with a hydrogen 1s orbital to form a second sigma bond and a third sigma bond with another hydrogen. These other orbitals, the px and the py here, they can overlap now to form two new pi bonds. So in this case, I have 1, 2, 3 sigma bonds and 2 pi bonds. Here I have 1 sigma, 1 pi, 1 pi, 1 sigma, and 1 sigma. Notice that the pi bonds are perpendicular to one another. So here, this pi bond here is overlap mathematically to form a bond. And where the sigma bonds are actually linear, there are 2 electrons shared within that pi bond. If I look at a triple bond, I actually have 3 pairs of electrons shared. My sigma bond accounts for those 2 electrons. There's 2 electrons somewhere in this blue that are overlapping, and there's 2 electrons in this purple region. So a triple bond consists of 1 single bond and 2 pi bonds. In summary, if I take the atomic orbitals for carbon and I hybridize them mathematically, I take 4 orbitals, combine them, I get 4 new orbitals. And they can then overlap with other atoms to form single bonds. If I take only 3 of the orbitals and hybridize them mathematically, I take 3 orbitals, I make 3 new orbitals, I leave 1 orbital unhybridized. Now I can make a double bond where I have 1 sigma bond between carbon and 1 pi bond between carbon and carbon. For triple bonds, I only hybridize 2 of the atomic orbitals to make new hybridized molecular orbitals. In this case, I form 2 new sp hybridized molecular orbitals, and I have 2 unhybridized dumbbell-shaped molecular orbitals. In the case of ethine, between carbon and carbon, I have 1 sigma bond made by the hybridized molecular orbitals. I have 1 pi bond represented by blue, and I have a second pi bond represented by the purple here. Okay. So, what about the bond angles here? Both from a mathematical standpoint and from an experimental standpoint, single bonds, which are sp3 hybridized molecular orbitals, have a geometric angle of 109.5, which is tetrahedral. If I look at double bonds mathematically, I have hybridized sp2 orbitals predicting a 120 degree angle, and that's going to be trigonal planar. Remembering that one of these bonds is a sigma bond made up from the sp2, and one of these bonds is from the unhybridized molecular orbitals, which makes up the pi bond. If I look at acetylene, or a triple bond, one of these 3 bonds here is a sigma bond made up by the sp2 orbitals from each carbon. The other 2 bonds are made up from the unhybridized p orbitals. Mathematically, we predict 180 degrees. Experimentally, we measure 180 degrees between hydrogen-carbon-carbon or carbon-carbon-hydrogen. If I look at the number of bonds versus bond strength and bond distance, I find out the more bonds I have, the stronger the bonds are. So for example, here, if I have 3 bonds between carbon and carbon, that's stronger bonds than 2 bonds between carbon and stronger than 1 bond between carbon and carbon. So the strongest bonds are actually shorter, so the more bonds I have, I pull those 2 carbon atoms together. So as bond strength decreases, going from left to right here, my bond length increases. So a carbon-carbon single bond is longer than a carbon-carbon double bond and is longer than a carbon-carbon triple bond. The greater the electron density in the overlap region, the stronger and shorter the bond. So if I look here at an sp3 hybridized carbon, it's longer and weaker. And I look over here at an sp3 to an s, an example, carbon to a hydrogen, there is actually more overlap mathematically between an s orbital and an sp3 orbital, so that bond is actually shorter and stronger than a carbon-carbon bond. How does hybridization affect bond length and bond strength? Another way to look at that is that if I have more S character, it's going to be a stronger bond. So if I look at carbon-hydrogen, and if this were an sp carbon, meaning I have a triple bond off here to the left, I have 50% of that bond is S and 50% is P, so it's a strong bond. If I look at this carbon, and if this one were sp2, meaning there's a double bond going off in this direction, this bond right here is actually only 33% S, so it's a little bit weaker. If I finally look out here to sp3 hybridized carbon, where there's only a single bond coming off of this carbon right here, that this bond is only 25% S character, and so it's the weakest. The more S character in the orbital, the stronger and shorter the bond. So sp orbitals are shorter and stronger than sp2 and shorter and stronger than sp3. If I look at bond angle, I notice that for a 25% S character in single bonds, I have 109 degrees. For sp2, I have 120, and for sp, I have 180. That's just a trend here, okay? So the more S character, the greater the bond angle. Just a notable trend that scientists sometimes use. In summary, if I look at these three different scenarios where I have carbon-carbon single bonds, carbon-carbon double bonds, and carbon-carbon triple bonds, and I look at both the carbon-carbon bonds and the carbon-hydrogen bonds, for the ethane, where all my bonds are single bonds, the molecular orbital hybridization around carbon is sp3. I have 4 sp3 hybridized molecular orbitals around carbon. Each of them has a 109.5 degree angle. My bond length between the two carbons is 1.454. The bond length between my carbon and hydrogen is 1.10. So I have a shorter bond between carbon and hydrogen than I do between carbon and carbon. And that reflects as in my bond strength. The shorter the bond, the higher the strength of the bond. I have 101.1 kilocalories. I have 90 kilocalories, which is a little bit less. If I look at ethene, where I have a double bond between carbon and carbon, 3 of these bonds around carbon are sp2 hybridized. 1 is still an unhybridized pi bond. I predict an angle of 120 degrees. My bond length now is 1.33 angstroms between the carbons, which is lower than the sp3 hybridized orbitals in single bonds, and so my bond strength is increased. If I look at the bond characteristics in the carbon-hydrogen bonds in ethene, I can see it's very similar to that of ethane, but a little bit shorter, which means my energy is a little bit higher. If I look at triple bonds now, one of these bonds between carbon and carbon is an sp hybridized molecular orbital. The other 2 are unhybridized p orbital overlaps. I predict a molecular geometry of 180 degrees. My bond length is now 1.2 angstroms, and so therefore my strength of my bond between the 2 carbons is greater than a double bond and greater than a single bond. If I look at the hydrogen, I'm also a little bit shorter for an sp hybridized overlap with an s orbital, and therefore my bond strength is higher. In summary, the shorter the bond, the stronger the bond. The greater the amount of electron density in the overlap region, the stronger the bond. For example, a carbon-hydrogen has more overlap than a carbon-carbon. The more S character, the shorter and stronger the bond, and the more S character, the larger the bond angle.